This question has to do with titrations, and we're looking at today what happens when there's a slight excess in a titration. And the question for this calculation is, calculate the pH when the following quantities of 0.1 molar nitric acid have been added to 25 mLs of 0.1 molar potassium hydroxide solution. So it's a strong acid and a strong base being mixed. And part B of the question asks what happens when you add 25.1 mLs to the base. So what happens is there's a slight excess of acid, a slight excess of the strong acid. And we recall that whenever a strong base and a strong acid are mixed, the result is an excess of, well, in this case, an excess of hydronium ions, an excess of protons, and a salt. And the salt is neutral, has no effect on the pH. So we start off our calculation by listing how many moles of potassium hydroxide are present. And we add a slight excess of the nitric acid, so that we end up having that much extra H plus in solution. We recall that the total volume of the solution now is the sum of the two volumes that were used in the titration. We started off with 25 mLs of potassium hydroxide, and you added 25.1 mLs of the nitric acid. So now the total volume is going to be 50.1 mLs, and that's how we find the concentration of the H plus. We have this much excess H plus in that much volume. It gives us this concentration. So to find the pH, plug it into the pH calculation. pH equals negative log of H plus. We get 3.71 as the pH. So you'll notice that there's no buffer present. That's why the pH changes so dramatically in such a short time. If you look in the previous video, you'll see that the pH was at 10.31 just before equivalence. Right after equivalence, it drops dramatically to 3.71. So in the space of 2.2 mLs of added titrant, the pH has changed from 10.31 to 3.71. This huge change of pH at what is called the equivalence point, when added acid exactly equals base that is present, is easy to detect using chemicals that change color with changes of pH. These substances are known as indicators. Indicators can be found that will change color at different pHs for different applications. Phenolphthalein, for example, the one that we would use in this titration, and is traditionally used, changes color from colorless to pink in the pH range of 8 to 10. So it is appropriate to use in the titrations of acidic samples. It's colorless in acid, and it turns pink when the solution starts to become basic. The end point of the titration in such cases is presumed to occur upon the first persistence of a faint pink color. Phenolphthalein is reddish or pink, or even fuchsia when there's a lot of it. Perhaps bromthiamyl blue is also an appropriate indicator for the titrations involving strong acids and strong bases, because bromthiamyl blue undergoes a color change from yellow to blue in the range of 7 to 8. So it's closer to the equivalence point for a strong acid, strong base titration. Now what happens when you have a weak acid, strong base titration? When you titrate a weak acid with a strong base, you're going to take all of that acid and turn it into its conjugate base. So for example, if you're titrating acetic acid, as you're adding the titrate, you're going to convert the acetic acid into its conjugate base, the acetate anion. At the end point, all of the acetic acid has been neutralized by the base, and all that you have in solution is the acetate anion, which is a weak base. So what's going to happen is that weak base is going to pull the pH up. At equivalence of the titration of a weak acid with a strong base, all of the weak acid has been converted to its conjugate base form. The conjugate base has the ability to pull a proton off water. Misspelled. So the result is a pH above 7 at the equivalence point of a weak acid strong base titration. So when you titrate a weak acid with a strong base, the pH is going to be above 7 at the equivalence. On the other hand, if you titrate a strong acid with a weak base, if you titrate a weak base with a strong acid at equivalence, you will get a slightly acidic solution, because the conjugate acid of the weak base is going to donate some protons into solution, and the pH will therefore be below 7. Now, so to work out an example where this happens, we're going to refer to the text, page 737, practice exercise in brown. It says, calculate the pH solution formed by adding 10 mLs of 0.05 molar sodium hydroxide to 40 mLs of 0.025 molar benzoic acid. So the benzoic acid is a weak acid, sodium hydroxide is a strong base. So this is a weak acid, strong base titration, so we will expect that the pH will be slightly above 7 at the end. In B, calculate the pH in the solution formed by adding 10 mLs of strong acid, hydrochloric acid, to 20 mLs of 0.1 molar ammonia, which is a weak base, so it'll be slightly acidic after equivalence. And here is where we work out the examples. In the first instance, we start off with 40 mLs of 0.025 molar benzoic acid. We add 10 mLs of 0.05 molar base, which is going to react with this and use up the HB, converting it into B minus. What we've done by doing this reaction is generated a buffer system. So we've also have to take into account the fact that the total volume is now going to be 40 plus 10, or 50 mLs. That's why I use an IRAC table for this calculation. It makes it easy to keep everything straight. So the final concentration of your acid is going to be 1.0 times 10 to the minus 2, and the concentration of your conjugate base is going to be 1.0 times 10 to the minus 2 at this point as well. This is not reaching equivalence, so it's not exactly an example of a weak acid strong base titration where you reach equivalence. It's one where it's only halfway to equivalence. So this is a buffer system. You have an acid and its conjugate base in equal amounts in a solution. So because a buffer system has been set up, because of equal amounts of weak acid and its conjugate base are in solution, we can use the Henderson-Hasselbalch equation to do the calculation of pH. Recall that pH is equal to P.8 plus log of the conjugate base plus the acid. In this case I use B because of the benzoic acid. The quantities are equal, so this is going to be equal to 1. Log of 1 is 0. So the pH is going to equal to the pKa. And the pH of this solution ends up being 4.2, even though a strong base has been added. Normally, if you were to add a strong base to a solution containing a weak acid, if you were to add a strong base to a solution containing only water, the pH would be way above 7. But in the presence of this weak acid and the fact that you haven't added enough to reach equivalence will ensure that the pH remains acidic. I just want to put a note as an aside, an IRAC table is preferable in this case because changes of volume are taking place during the titration, which will affect your concentration. So just to keep everything straight, it's good to write it all down, and then at the end you calculate the concentrations. If you don't like using an IRAC table, you can just use an ICE table, but make sure that you take into account that all of the things that you write down are concentrations. So you'd have to write this number and not any of this stuff, or else you get the wrong answer. You would write this, and that into the ICE table. Sorry, this number, and that number will be written into the ICE table, and you keep all these calculations on the side. Okay, in the second half of this question, we were asked to calculate the pH in a solution formed by adding 10 mLs of 0.1 molar HCl, a strong acid, to 20 mLs of a 0.1 molar solution of ammonia, which is a weak base. So again, we're doing a titration where it's only reached halfway to the equivalence point. So we're going to set up concentrations that are equal. We're going to have equal concentrations of the base and its conjugate acid. So again, that's going to, whenever you see equal concentrations of the conjugate base and the acid, or the base and its conjugate acid, or the weak acid and its conjugate base, you know right away pH is going to equal to pKa. So I wrote here pH equals pKa because when HA equals A minus, then the log term of the Henderson-Hasselbalch equation will have the same numbers in the numerator and the denominator. That equals 1. Whenever you have the same two numbers above and below the fraction sign, then you know you're going to get 1, and log of 1 is always 0. So there's not going to be any change from the pKa. The pH will equal the pKa. The Kb for ammonia is 1.8 times 10 to the minus 5. This is the only tricky part here. The Kb is 1.8 times 10 to the minus 5. That means the pKb is 4.74, and pK values can also be related like pH values to the number 14 because all the reactions are taking place in aqueous solution. So the pKa is equal to 14 minus the pKb. So the pKa for ammonia is 9.26. You enter that into the Henderson-Hasselbalch equation, log of 3.3 times 10 to the minus 2 over 3.3 times 10 to the minus 2, where the A minus is symbolizing ammonia and the HA is symbolizing ammonium. Log of 1 is 0, so the pH equals the pKa, and in this case you get 9.26. Just recall again, an IREC table is probably the best way of calculating the different values in this equation because you're getting a change of volume as the titration takes place. So you're adding 20 mLs to 10 mLs. Just recall that you have 30 mLs at the end when you calculate the concentrations. If you don't use the IREC table, if you use the ICE table, then you have to enter in only concentrations. So this is a concentration, this is a kind of concentration, and so is that. And you don't really have to even use an ICE table if you don't want to either, just as long as you can recall what the final volume is and how much of either the acid or the base is left in solution.